Okay, so thank you. My name is Marko, and today I will be talking about the transition from analog to digital meteor spectra. And this is a study still in progress, which I'm doing as part of my PhD study under the supervision of Dr. Jiří Borovička. So I will talk in general a bit about the meteor spectra, briefly about the equipment which was previously used and is used now. And I will try to give you a full walkthrough the whole analysis process, starting with obtaining the spectrum from the image and then doing the analysis itself. And finally, I will present some results and have a small discussion about it. So to begin with, what we're actually observing is two separate spectra, but we see their superposition. So one spectrum corresponds to the meteor heads at temperatures about 4,000 to 5,000 Kelvin. And these are mostly neutral lines of these elements. And we also have the second spectrum corresponding to the shock wave at higher temperatures, about 10,000 Kelvin, which has singly ionized lines of the elements listed here, and is usually only present in faster meteors. And it's very important to note that these observed line profiles are actually instrumental, meaning that they depend on the used equipment, and we need to somehow characterize this data and to get some physical interpretation out of these results, we need to create a synthetic profile. And this is done using a weight function, which is a convolution of a Gaussian and Lorentz function. So basically it's described by two parameters, the Gaussian width, which dictates the width of the profile, and the Lorentz factor, which dictates the shape of the wings. So, so much for theory. Let's look a bit about the equipment. So on the left image, you can see the 6 analog cameras, which were a single station system operational from 1960 to 2018. This was located in Meteor, and you can see the rotating shutter in front of the cameras. These cameras had photographic plates, and oh yeah, so much for that. But on the other image, you can see the SDAFO and DAFO systems, which are currently operational. And they have 12 stations. Well, the SDAFO system has 12 stations across the Czech Republic, Slovak Republic, and Germany. And these cameras are Canon EOS cameras equipped with CMOS sensors. And so there's a lot of technical stuff here. I will not be going through every single thing on the list. However, I will point out some key differences. So we have a full night exposure time that was used for the analog cameras, and we have 30-second exposure time for digital cameras. You will see in a few slides where this is quite important. Probably the most key aspect here is that both the resolution and the dispersion of the digital cameras is about 10 times worse than that of the analog cameras which were previously used. So why exactly did we decide, despite that, to switch to digital? We have a larger field of view, a larger spectral range that includes the near infrared region. The cameras are less susceptible to moonlight and weather conditions. They don't require an on-site operator. Just in general, it's much more practical and easy to acquire data and use it and share it. So it's not this system is operational since 2015, and since that time, we recorded more than 670 spectra, and if you compare it to 240 spectra recorded in 58 years of operation, you can see the difference in the amount of data we're working with. But so much for the equipment. This is what a digital spectrum looks like. So we have a Meteor at which is the point. Okay, so this is the spectrum. You will see a nicer image at the end, but in any case, the analysis starts by taking a look at the main image and a look at the background and seeing if there's anything obstructed or out of focus, or in general if the spectrum is usable. Once we determine it is usable, we can open it up in TIFF formats in Jiří's code, and there we can apply the light field correction, subtract the dark frame, do astrometry and photometry. I will not be going into details about how this is done. But once we do that, we can locate the spectrum on the image itself, and we can adjust the scanning area to fit the observed spectrum. And once we make sure that it's adjusted properly, we can go ahead and scan the spectrum on this image. And while this is being done on the main image, we are also loading the background image into the program, doing the same analysis, the same procedure on it. And we're scanning the same area shifted by the amount the stars shift during the 30 seconds of exposition time. And then we scan the same area and we subtract it as the background. Which we can do for digital cameras because we have a 30-second exposure time. But for analog cameras, this was not possible because we had whole night exposure time. So what we will do in such cases, we will shift along the star trail and take a portion of the image as close as possible to the meteor spectrum itself, but with relatively clear background, and we will subtract that. And once we do this, we obtain something like this. So this would be an example of a digital spectrum, and this would be an example of the analog spectrum of the same meteor observed from different stations. So you can see a big difference in resolution and quality. So we need to somehow overcome this issue and still get reliable results. So from here on out, the analysis is done in Synthwith software, which I personally developed over the past 2 years. And the analysis starts by loading the theoretical line positions and the assumed line intensities. And once we have that, we start off by selecting only the lines which are clearly visible and can be recognized in all of the spectra. We make sure that these profiles fall within the boundaries which are preset. We can shift manually the spectrum until this is the case, and it requires very little time to do so. And once this is done, the program itself recognizes the profiles and fits these lines. And this can be manually adjusted later, though it usually requires a very small shift. Once this is done, we are happy with all of the identifications. We can go ahead and plot wavelength shift against wavelength and describe this dependency by a polynomial fit. That way we can calibrate the wavelengths. However, this is still just a rough wavelength fit. To have a proper wavelength fit, we need to include all the lines which we have and repeat the process. And once we do that, we have a much better wavelength fit, and we obtain something like this. But we're still not done. We still need to calibrate the spectrum for spectral sensitivity, and finally we need to determine the dependencies of the Gaussian Lorentz factor on wavelengths. And we can do this either polynomially or manually. And once we're happy with the selection, we go ahead and refit the intensities with the newly determined parameters. So this would be the final results for an analog spectrum, and the same final results for a digital spectrum. And to really compare them, we need to plot them with same dependencies of the Gaussian Lorentz factors or the same profile shapes. I will not describe in detail how that is done. You can ask me later if you're curious about it, but these are the results we obtain once we do that. And you can see right away big discrepancies. Let's start from the beginning of the spectrum. Between the black line, which is the analog camera, and the other lines, which are the digital cameras. That is due to a wrongly calibrated spectral sensitivity for the analog cameras, and we are currently looking into it, and we will fix it hopefully. But in general, the profile relative intensities are what we're really interested, and it seems that the relative intensities are consistent throughout. There are some larger differences in this region. However, the digital cameras have the smallest spectral sensitivity in that part of the range, so we assume that it is within measurement errors. And as you can see, in the rest of the spectrum, it's much clearer and more consistent. And this is an example of a faster meteor, which has also some continuum, and the secondary spectrum also contributing. And here you can see some larger discrepancies between some of the profiles, and it's not a problem if we want to scale the whole spectrum with a single factor, because this can just we're only interested in the relative line intensities, not the absolute ones. However, if we need to calibrate the different parts with different factors, that means that there's an underlying issue throughout it. However, these differences we feel are coming from the slightly wrong manual determination and subtraction of the continuum. And since it's very wide profiles, very small difference in the continuum will result in a very significant difference in line ratios. However, if we scale each segment individually with different factors, you can see that we're getting pretty consistent intensities. So this is something we'll further look into and see if there's other underlying reasons or if it's only this. And also it needs to be pointed out that this is not the physical fit. This is the mathematical fit to determine the Gaussian-Lorentz factor dependencies. And these comparisons are not some final results. They're just an intermediary checkpoint to see if everything is done correctly. And I'm not going to go through the whole spectrum, but you can see that it's more or less consistent as well in the different parts with the adjusted scaling factor as well. There are some larger differences and we're looking into it. So this is definitely something else, maybe due to the grading or we're still looking into it. In any case, this is the current status. And we have completed the software development, the wavelength calibration, partially automated the process, and we're obtaining these dependencies, which we're interested in. However, we still need to improve on the spectral sensitivity of the analog cameras, identify the continuum better, and in general, solve some issues. So not to bore you with any other technical stuff, these are some references, and I thank you for your attention and leave you with a nice image of spectrum.